organizers for organizing this wonderful conference, and thank you for giving me the opportunity to present our work on the 21 centimeter forest from the epoch of reionization and our exploration with Gish and Shriyas Tendulkar, our exploration on the prospects of detecting this signal and its potential to constrain the thermal and ionization state of the IgM. So I will start by briefly describing what the 21 centimeter forest is. Benedetta did that, I think, 2 days ago, but I'll go through it again. So it's a series of absorption features in the spectra of some distant radio loud sources, which arise from the neutral hydrogen structures along the way due to the hyperfine structure of the neutral hydrogen atoms. And as you can see here in this animation, in the bottom panel, you see these absorption features which correspond to the kind of overdense regions, but mainly neutral and cold. Okay, so this signal is complementary to other 21 centimeter line observables, and this is because, like I said, you use as your radio background source, you will use these radio bright point sources like I don't know, radio loud quasars or gamma ray bursts instead of cosmic microwave background. So, and because of that, what you need for detecting this signal is high signal to noise spectrum, radio spectrum of these sources, which in principle should be less complicated to detect. But of course, this signal has its own challenges, such as if we have good number of radio loud sources at these higher redshifts. And it is complementary to the Lyman alpha forest as well, because like I said, the signal will probe these neutral, dense, and cold regions in the IgM, as opposed to the Lyman alpha forest, which probes these ionized and hot regions. So with 21 centimeter forest, we might be able to probe very, very different IgM, and as well redshifts higher than 6. So, of course, I'm a big fan of 21 centimeter forests, obviously, but why you should care as well are quite a few studies that suggest that with 21 centimeter forest signal, you might be able to constrain some astroparticle physics, like the nature of dark matter, probe small-scale structures like mini halos, constrain supermassive black hole growth models, and constrain thermal state of the IgM. We want to extend that to the ionization state of the IgM as well. Okay, so hopefully I have persuaded you now that it is really worth our time and effort to actually study this signal, but let's discuss why now may be the right time to push even more. Okay, so one of the reasons is on the theoretical front in the field, let's put it that way. So some recent Lyman alpha observations seem to require reionization to be completed rather late, so at redshift less than 5.5, so this has been mentioned before at this conference. Why is this relevant for 21 centimeter forest signal? It's because in this scenario, you expect large islands of neutral hydrogen to be present at redshift as low as 6. As you can see here in these 2D slides of the ionization state of the IgM at redshift 6, so this is from Sherwood Relics simulations. You see these dark regions here, they correspond to the gas that has not been reionized yet. So it is expected to be cold and neutral, right? So, and if you have that, there is a possibility of detecting strong 21 centimeter forest absorbers. Even at redshift 6, which would be nice, because at lower redshift you expect more radio loud sources, at least in terms of the number. And speaking of that, another improvement or advancement in the field is the number of confirmed radio loud quasars at redshift higher than 5.5 has almost tripled in the last 4 years. So now we have around 32 radio loud quasars at these high redshifts, which means that we have a good number of targets that we can point our radio telescopes at. And hopefully these numbers will increase with surveys like with LOFAR, so future looks encouraging, I would say. And another improvement is on the instrumentational front. For example, GMRT has improved its sensitivity. It was upgraded to UGMRT. And so here I show a plot of the sensitivity versus observed frequency. Higher sensitivity means, of course, better because the telescope noise will be smaller. And at these frequencies that I show in this red, in this red region here, so they correspond to the redshifts of these radial loud quasars that I showed you on the previous slide. And you see that at these frequencies, UGMRT has better sensitivity than, for example, LOFA. So we will go with this one in the next, in the rest of this presentation. But also, of course, we all look for the SK, which will have obviously much better sensitivity, like 6 times better. So, so yeah, again, the future looks encouraging and exciting. Okay, so let's discuss different ways of different strategies, how one might try to or attempt to actually detect 21 centimeter fluorescent signal. So an obvious way would be you go for a direct detection of individual absorption features in the spectra of these distant radial loud sources. So here I show an example of simulated 21 centimeter fluorescent spectrum. This is purely just the signal at the redshift 6 using, or this was based on the 21 centimeter far simulations. And if we include some of the instrumental features, like the telescope noise, what you get is this black curve here. So this is a signal plus the noise. Sorry, so we assumed observation by UGMRT over 500 hours, pointing at this laser discovered by Beladita 2020. And yes, I have to admit, this doesn't look that great, especially because, for example, if you compare these two features, I mean, it is very easy to confuse like which feature comes from actually signal and which one comes from just the noise. But this motivated us to try and look for a different way to try and detect this signal. And in particular, we look at the statistical detection of 21 centimeter forest, and in particular, we are going for 1D power spectrum calculated from the 21 centimeter forest spectrum, which is shown here. The solid curve corresponds to the median value over calculated from 1,000 lines of sight, and the shaded region corresponds to the 68% scatter around this curve. So this is just to give you some intuition how important the sample variance is. Okay, and so this is purely just a signal, so that orange curve that I showed you on the previous slide. So if we compare this with some noise limits, so the upper pink curve corresponds to the same observational setup I showed you on the previous slide, so UGMRT, 500 hours of observations. The bottom one is for SK1 low, 50 hours of observations. You see that at large scales, so small k, so yeah, just somewhere here, you see that the signal is actually above the noise limit. So I guess this looks kind of encouraging that we might be able to actually detect this at these large scales, so small k's. But of course, the signal itself will depend on the thermal and ionization state of the IGM. So in our modeling, thermal state is dictated by the these FX parameters, so the efficiency of the X-ray background radiation, and which was mentioned here before, and XH1 is just the mean neutral hydrogen fraction. Okay, so given that the signal is dependent on these two, or sensitive to these two parameters, let's see if we in the future manage to measure this signal, can we constrain these two parameters? So to do that, we assumed observation of 10 spectra of around 22 megahertz of bandwidth, and we fed this into MCMC, and this is the result what we get for UGMRT 500 hours. So the blue is just the posterior distribution. Orange cross corresponds to the true values that were used to compute the mock observation, and the pink lines correspond to the inferred values. So you can see that even with these observational set, we might be able to actually constrain both of these parameters. We also assumed observation by SK1 50 hours. You see that they don't really change, or they are not really different that much. And so from this we imply that it's not the telescope noise that is the limiting factor, but actually sample variance. Okay, so we also did this for different parts of the parameter space. So So this is for UGMRT again, but so maybe the actual potential power of this observable doesn't lie in getting the actual measurement of these two parameters, but maybe if we get a null detection of the signal, we might be able to translate this into disfavoring some of the regions in the parameter space. And if we compare this to some actual measurements from the Lyman alpha observations, you can see that we might be still able to maybe disfavor some of the values that are still allowed by the Lyman alpha or current observations. So yeah, so this is the summary. Just to maybe quickly sum up, I hope that I have persuaded you that 21 cm4s is a unique probe of our universe, for example, constraining thermal and ionization state of the IGM, and the prospects of detecting it are improving. And yeah, so thank you for your attention.
Yeah, sorry. So you mentioned null detection at the end. So I'm just wondering, because you need it to be neutral and cold.
Yes.
And the very neutral and very cold is already starting to be, well, if we believe this, but it's already starting to be constrained by upper limits from here, right? So I guess I have to find a question now. So are you? So because in maybe my image in my head is wrong, but in my head, sort of the standard default reionization history means that during reionization is actually an emission, the neutral media, but doesn't have to be always the case, right? But so are you more focusing on null detection then, or are you disagreeing with my statement?
Okay. I honestly believe that a null detection might give us more constraining power actually to, disfavor some low FX values, for example, or some low temperatures if you want to translate it into that. But I don't think I can tell too much or any specifics about that. This is, I guess, the next step that I really want to do to explore these possibilities, and then put that in paper to like something more specific. But I think this would be the way.
Sorry, just a naive question. How do they, if they do, foregrounds play into this?
Okay, I don't think I have actually mentioned that. I guess that's one of the main advantages over the other 21 centimeter line observables that so like I said, you don't compare it with CMB, but it's some bright radial out source. So I don't think the foreground should be that important. Anyone can correct me with that. I'm not observer, but that's definitely one of the main advantages over the other observables.
Foreground will still contribute to the variance of these fluctuations around the Means even if you assume that they will still contributing because they are emitting in the same wavelength.
Okay. Fair. Okay.
In any sense, if you
Okay.
Expectation value is zero, but
the variance will be there.
Okay, I see. Okay, yeah. Well, it's something to think about in the future.
Alright, last question, Maxi.
So, thanks a lot. Maybe science fiction again then. Is there the prospect with SK then to detect like in individual spectra for us, like the first method at all? Like you said 50 hours of SK was 500 hours of fusion. About 200 hours of SK.
I mean, I don't have plots here. Now I can show that to you later. It looks better than what I showed you with the UGMRT. I guess it might be possible. Of course, if you go to I think it looks nice if